So this video is going to take us through a sample problem that allows us to, using experimental data, determine our rate law. And so the rate law we're looking for is of the form our rate equals rate constant K times the concentration of some reactant A raised to exponent times the concentration of B raised to some exponent. And so really what we're trying to find is the values of A and B, and how we find that is to look at different experiments. So we're actually going to compare a couple experiments from this data right here, and there it is. And so basically what we do is we look at experiments where things are held constant and other things are changed. So really you only have two reactants. So if we look at experiments 1 and 2 here, well, concentration of A is changed and the concentration of B is held constant. Therefore, any rate effect is due solely to A only. So concentration changes in A. And so we can say the same thing for experiments 3 and 4. So in experiments 3 and 4, concentration A is held constant and the concentration B is changed. So any rate change that we see over here is due solely to the change in concentration of B. So that's what we do. So let's go through this. So basically what we're looking at, we're going to look at effects of changing the concentration of A first. So there's experiments 1 and 2. Notice that B is held constant. And so what we're looking at here is rate is proportional to, and we've mentioned that before, the concentration, initial concentration of reactants, and so in this case it's A raised to some exponent A, and we're trying to find A. And so in this reaction, if we look at it, in between reactions 1 and 2, we affected a rate change that essentially doubled. So we went from 0.2 moles per liter second to 0.4 moles per liter second. So a change in the concentration of A, rate increased by a factor 2, it doubled. What did we do to the concentration A? Well, we did the same thing. We increased it by a factor 2, we doubled it. And so by inspection, A equals 1. And so that is the order of reaction in A. It's first order. Now, we can look at our second set of experiments. So this was, I believe, experiments 3 and 4, where we held the concentration of A is the same, and we've changed the concentration of B. And so now we're looking at is rate effect caused by a change in initial concentrations of B. And so in this case, we get to look at rate 2.4 increased to 2.4 from 0.6. So the rate increased by a factor 4. And what did we do with concentration? Well, we only doubled concentration. So again, by inspection, B must equal 2. It's second order in B. And so we can write a rate law for that now. R equals K times the concentration of A to the 1, first order in A, times the concentration of B squared. So there is the rate law. Overall order is third. 1 plus 2 equals 3. Okay? So that's how you use data to determine initial rates. Well, we can confirm this with other data. So let's do that. Let's look at, we have enough information to do another quick check. And so if we look at experiments 1 and 3, we can still look at the effect of A. And so with experiments 1 and 3, what we're looking at here is rate proportional to change in concentration of A. Notice B is still held constant. B is still 0.1. And we're going to find that exponent A. And so rate went from 0.2 to 0.6. So we tripled. Rate went up by a factor of 3. And what did we do to concentration? Well, we tripled it. And so A, thankfully, still equals 1, as it should. Well, we can also look at experiments experiments 3 and 5. So with experiments 3 and 5, what we're looking at now is a rate effect caused by a change in B. Right? So experiment 3, concentration of A is held the same, 3 to 5, whereas concentration of B is changed. And so rate has changed by, in this case, a factor of 9. Well, how did I get that? 5.4 divided by 6.09. All right? just in case you're wondering how you can, sometimes the numbers are a little hard to figure it right away, so just divide the larger by the smaller and you get a factor. What did we do to the concentration of B to affect that 9-fold increase in rate? We tripled it. And so again, thankfully, B still equals 3. So it's still R equals K A B squared. All right, so that's useful information. It's always, if you're worried about it, you can always, if you have enough data, you can always do a second check. Now, last thing I want to look at here is what about the value of K? So calculation of K is important, as you'll see in a later example, but we can easily calculate the value of K. We have the rate law, R equals K A B squared. So what does K equal? K equals rate divided by the concentration of A times the concentration of B squared. And now we can just plug in. So it doesn't matter what numbers you plug in. You just pick an experiment and you put in the requisite data. Remember, it's a constant. All of these different experiments should yield the same value of K. So let's look at this. So 0.20 moles per liter second divided by concentration of A was 0.1 moles per liter. Concentration of B was 0.1 moles per liter squared. Don't forget that. And so when we plug and play there, we get, so that number, when we after you plug it into the calculator, comes out as 200. And what about the units? So this is so important. I'm going to do it in red pen and I'm going to show you. So unit analysis is really important with rate constant determination. So what we have is mole per liter second divided by mole per liter times mole squared per liter squared. If we simplify that, it becomes mole per liter second times liter cubed mole cubed. We take all of those under the numerator, we take the reciprocal of it. And so that simplifies down to, we're going to divide it, this one's going to be gone, we're going to have 2 of these left, mole is gone, we're going to have 2 of these mole left squared, and so what we end up with units are liter squared per mole squared second. And so there's the unit. So the actual rate constant K is 200 liters squared per mole squared second. So it's important you realize the calculation of the rate constant is important, especially the units. And typically on my tests, you get 1 mark for the number and 1 mark for the unit. So you do have to analyze your units carefully. Now, it shouldn't make a difference which experiment you pick. So why don't you take a minute, use this experiment here, experiment number 5, and calculate the rate constant K in the unit using those values and see what you come up with. So how'd you go with that one? Hopefully you would have got something that looks a bit like this. So again, important units, liter cubed per mole, or sorry, liter squared per mole squared seconds, and the correct value. And so that's how you carefully work through determination of the rate constant K and the unit for the rate constant K. And that concludes this video.